introduction, a review to quantum computing. Some of you saw that before, but it's a good time to review, right? So what is quantum computing? I would say quantum computing uses two very important phenomena, superposition and entanglement, right? You probably don't know what it is. We will review again later, superposition, entanglement. And in my opinion, interference is very important because quantum computing promises to do a lot of computation in parallel. However, you cannot get all the information in a reasonable time. How do you get the information you want to use? You design an algorithm so that it causes some interference and it can give you an answer, okay? So superposition, entanglement, and interference. There are two major types of quantum computing. One is the gate-based, right? That is, for quantum computing architecture, our mindset will be focusing on gate-based, but however, all the math we are learning can be used for quantum annealing also. A gate-based model is like this. You have a circuit. This is a quantum computing circuit, right? Exclusive NOT gate, Hadamard gates, identity gates, Hadamard gate measurement. You go through all this operation, you get the answer you want. Another is quantum annealing. It's more like optimization. It is through a configuration of your system and then the energy. Our goal is to find the minimum energy. Why we want that? Because we map the physics to the problem we want to solve. For example, the traveling salesman problem. What is the shortest path that I can visit all this city? Right? That is very important. For example, for Ford, the car manufacturing company, how do they distribute all their car or components, right, in the lowest cost to every city in America? Should I set up a station in San Jose or just let it be in Sacramento? May be good enough, right? Those are what we call NP-hard problem. And if you can map this problem into the physics of quantum computer and then let the system evolve and then find the minimum energy, then you solve the problem. So the difficulty is to map to the system, right? That's so-called quantum annealing. And one interesting thing is that in this formalism, in this hyperspace, you might also have quantum tunneling. It's not a tunneling into real space, but the system is allow you to tunnel from a local minimum to a global minimum. So for those who do machine learning, you immediately find that, well, maybe this is something we can use for machine learning. Because machine learning is an optimization problem. And indeed, this is related, right? We have quantum machine learning and some optimization problem. This all can be done by the same hardware, okay? I just reused this slide from other class, so that's why this talk is for gate-based. But however, in terms of hardware, it's applicable. We can use it for drug design because doing molecular simulation is very difficult, very time-consuming. Right? Your quantum computer will be fast, secure communication, optimization, and finance. Okay? So the keyword is superposition, entanglement, interference. You don't know what it is now, you need to memorize. Two types, gate-based and quantum annealing. What is superposition? Right? So first of all, classical computer, we know that we representing everything as 0 and 1. 0 and 1 are what? State. Okay, call it a state. I can use head and tail, right? I can use happy and sad, or a transistor on and off, right? To represent the information in the state. We all happy with that, easy, right? Even the ancient people, they use the knot on the string to represent the state, right? How many sheep you owe me this month? Just how many knots? Quantum computing also use the state. But what state is that? They start with something called basis state. So I also can have a basis state 0 and 1. This basis state, you can imagine just like the 3D space, I have the x hat, y hat, z hat, right? We have the unit vector, free of the basis state. So it's nothing special. I just put this in this so-called bracket notation, right? This is direct bracket, and you feel confused, but just take it for granted. It's just a way of writing something. I put in the bracket. It doesn't affect you from understanding that this is a state. Again, I can use happy and sad. How about transistor on and off? That can be used to represent quantum information if only care about the basis state. Then quantum computer is the same as classical computer. But quantum computer allows superposition. What does it mean? You can have a state that is a linear combination of two basis states. It's just like your 3D vector. Any vector is a linear combination of x, y, and z, right? For example, I can have a vector, maybe, let me call R. Right. I call it R. Let's say V, right? It is equal to AX hat plus BY hat plus C hat, right? This is classical. But I want you to understand that, yeah, every vector in the 3D space is a linear combination of these three basis states. Now, if I have a quantum computer, I also have two basis states, 0 and 1. Here I show a general state, alpha times 0 plus beta 1. Alpha and beta can be complex number, right? So this one is a state. It's just like saying that, well, this is not a true one, but it's an analogy. A spinning coin on your table. It is a linear combination of head and tail. Do you agree? But of course, I cannot implement a quantum computer with this, right? So some people use this as analogy. Now, in this class, unless you have time to study more, you need to trust me on this keyword, that any state can be a linear combination of the basis state. Okay, you can think more. You can think a lot about when I see the moon or when I don't see the moon, is the moon a superposition of there and there, right? Like the Schrodinger's cat, I don't look at the cat. Is it a linear combination of alive and death? You can think about that, right? But if you don't have time, you trust me, that is the superposition. So compared to the classical computer, I have superposition that I have many states exist at the same time. What does it mean then? In classical computer, if I have 4 bits, how many possible value, right? You have 4 bits. How many possible value I can represent? It will be 16, exactly, right? 0, 0, 0, 0, all the way to 1, 1, 1, 1, right? But in quantum computer, ignore this tensor product for now, I can have also 16 basis states, right? As I told you earlier, it's the same as the classical computer. The basis state is the same. However, I say it allows superposition. So I can have a state that is a linear combination of these 16 states. If I have n qubits, then I can have a state that is a linear combination of 2 to the power n basis states, right? Because 1 qubit, I can have 0 and 1. 2 qubit, I can have 0, 0, 0, 1, 1, 0, 1, 1 is as the basis state. Then if I have n qubit, I can have a linear combination 2 to the power n, right? Then what does it mean? Well, if I have 300 electrons, I use the spin. Each of the spin can spin up and down. Each of them is a basis state. Now I have 300 electrons. Of course, it has 2 to the power 300 basis state. If I form a state, general state, it will be a linear combination of this 2 to the power 300 basis state, which is 10 to the power 90 complex number, right? How do you describe the state of this 300 electron? You almost cannot describe that, because in this world, this universe, you only have less than 10 to the power 82 atoms. Even you can store one complex number in one atom, you cannot store the information of a particular state of 300 atoms. Okay? Similarly, you don't have enough storage system in the world to store that. This just to show you, yeah, superposition really powerful because you can have many different states. You can have a state which is a superposition of many basis states. Any questions? And quantum mechanics is linear. If I have a combination of all these basis states, I try to do an operation on them. effectively, I do the operation on each of these states, right? Use a not very accurate example. For example, I want to find what is 0 to the power square, 1 to the power square, or 1 square, 2 square, 3 square, all the way to 1 trillion square. In a classical computer, I need to calculate 0 square up to 1 trillion square in 1 trillion time. But in a quantum computer, if I can formulate it well, I can calculate all of them in one shot, because I just need to form a state which is a superposition from 0 to 1 trillion. And then use the function, do the square, right? Of course, not that simple, right? I just want you to see this. So it looks like it's a quantum parallelism. I can compute everything at the same time. The reason is because I can form superposition. I group everything together, dump into the machine. We don't know what it is, just like a spinning coin. Whether it is a head or tail, how do you know? When it is spinning, it's a superposition of head and tail. How do you measure it? You need to stop it, right? When I stop it, it either becomes head or it becomes the tail. And that is the difficulty of quantum computing. You actually don't know which it will end up, because it will end up randomly. So this is the measurement, right? Just like a general state, it is a linear superposition of 0 and 1. When I do the measurement, it either gives me 0 or gives me 1. I don't know what is alpha and beta. I don't know. The quantum state has such a rich information, but I don't know what is within each of these states. The only thing that it affects me is that the probability that I get 0 is proportional to alpha square. The probability I get 1 is proportional to beta square. So in principle, if you prepare the same state a lot of time, a lot of the same states and measure it many times, based on the statistic, you know what is alpha square and what is beta square. But you still don't know what is alpha and beta by this measurement, because -1 square equal to 1. Negative I square equal to 1. I mean the magnitude square, right? I square equal to 1. You don't have a lot of important information, the phase, okay? But that is how you do the measurement, right? Now, another thing we talk about is entanglement. Here is just a very high level, but later we will go deep a little bit in the second class. What is the meaning of entanglement? I just say that any general state is a superposition of some basis state, right? In this case, I have 4 basis states, 0, 0, 0, 1, 1, 0, and 1, 1. I actually can factorize it so that this one actually represents 2, or it's not clear, right? The reason I have 2 states is because I have 2 electrons. This is electron 1, this is electron 2. You can think about spin up, spin up, spin up, spin down, spin down, spin up, spin down, spin up, down, right? Both of them are spin down, right? So these are the possible basis states. Now I can factorize this so that it becomes electron 1 times electron 2, right? We'll talk about this later, the tensor product. But there are some states, no matter what you do, you cannot factorize them. And they are called the entangled state. Entanglement between the electrons, right? Let's see what it means. Here I have 2 electrons. I consider it as a system. And I assume it is at this state. Can you tell me what are the basis states of this system? Yeah, 0, 0, and 1, 1, right? Or spin up, up, both spin up, both spin down. It's just the basis. And then, but this state is a superposition of them, okay? Now, if I bring this electron 100 light years away, I separate them. If I don't destroy them, they are still acting as a whole system. They still have the same state. Now, what if I do a measurement on electron 1, right? I send the other electron to very far away. I measure the one on the Earth. I just told you how we do measurement. When you do measurement, it will collapse to one of the basis state, right? Either 0 or 1. Remember this one? When I do the measurement, it becomes 0 or 1. So the first electron, I measure it either spin up or spin down. Let's say I get spin up. But if it is spin up, since in the whole system, only this basis state has electron 1 spin up. This one is spin down, right? So I must get this states because the whole system collapsed to up. Then it means the electron, which is 100 light years away, will also spin up. I measure it at the Earth. I even don't know what happened there. And the light is not able to travel so fast. It takes 100 years to reach the electron. But whatever I do in the Earth will have an effect. You can say that far away. So that is something very interesting, right? We don't want to go into detail why or what are the implication. But it has such an interesting thing that Einstein called it the spooky action at a distance. Okay, this is called entangled state. I'm just giving a general overview, right? If you don't understand, that is fine. So we talk about this basic thing, and then what is a quantum gate? A quantum gate is something we try to operate the, we can say that the quantum gate is to rotate the state in its hyperspace, okay? So you might be rotating, a state is just a vector. So what we're doing is that the subject may be at a certain state. It can be at 0, at 1, or a linear combination of 0 and 1. And then we apply the gate. What is a gate? A gate is just a laser pulse or a microwave pulse. So you have spin, apply a laser or microwave pulse, then the property or the spin is going to rotate, to change. And that is the process of applying a gate. And people try to embed the hyperspace of the state in something called broad sphere, which we will discuss later in a lot of detail. This is very important. We'll do it in the first part of the class, unlike E225, we did it at the end, right? Now, because now it is very important. Basically, just like rotating the vector in this space. It's not difficult to understand. It's just like a digital circuit. What you are doing is like transforming 0 to 1, 1 to 0. But you only do it between 0 and 1 in classical computer. But now in quantum computer, you transform it between the linear combination of 0 and 1. So we can have 1 qubit gate, which is not very exciting, but very fundamental, very important. We spend a lot of time on that. That's to study how you rotate a qubit, what microwave pulse you need to do, what cavity you need to design, so that I can change it from the state 1 to maybe 1 plus 0 to maybe 0 minus 1. I did not normalize it. And then to maybe to 1. How do you rotate them? By rotating them, then you realize the implementation of the gate. And then you can use it in a quantum algorithm. Okay? But quantum computing is useless if you don't have 2 qubit gates. It means that this microwave pulse affects 2 qubits at the same time. For example, the control NOT gate. This is a state, basis state A, B. It can be, for example, 1, 1. When I apply an exclusive OR, it's going to be changed to 1, 0. Because when the first qubit is 1, it's going to negate the second qubit, the basis state in the second qubit. Okay? So by doing this 2 qubit gate, which sometimes called the entanglement gate, you will be able to form entanglement, which is very important, and that is how you speed up a lot of algorithm. Because if the qubits are not entangled, they are just like a classical circuit. There will be no benefit, right? One of the famous gates is called Hadamard gate. It's just like you start with 0, it becomes a superposition of 0 and 1. Think about classical computer. If you start with 0 and you get 0 plus 1, what is that? there is an error, right? Because for any register, you cannot have anything other than 0 or 1, right? If you return something, say is 0 plus 1, that is an error. Here, superposition is the the most important thing in quantum computing, okay? So what is you know what is a quantum gate? It rotates the state in the hyperspace. It has some property. Is that quantum gates need to be reversible. This is a LAN gate. If the output is 1, do you know what are the inputs? You don't know, right? Because the input can be 0, 0, can be 0, 1, can be 1, 0. So it's not reversible. You give me 1, I don't know what I need to give it. This one consumes energy. Quantum gates must be reversible. If you tell me this is a C0 gate, which you have not learned, 0, 1 must come from 0, 1. 1, 0 must come from 1, 1. So it's reversible. And this is very natural, because later you find that, as I said, quantum gates is a rotation of the state in their space. And that is like Schrödinger equation. You apply a pulse of energy, right, in this system, it will evolve. And everything, if you don't lose energy, not dissipative, you can go back in time. It's symmetric, right? It's time reversible. So you should be able to go back. If I say this is a quantum circuit, now I need to tell you that this is the flow of time instead of space. You guys know a lot of circuit design. How do you lay out an adder? Well, I start with the NOT gate, and then NAND gate, and then whatever gate, ALU accumulator. You go from left to right. You look at your chip. You do have the transistor go from left to right. And you draw the circuit, right? Now, when people show you this one, now it's not. It's not really I have a physical gate at this space, and then go to the next space. Quantum computing is the qubit-centric. The qubits sit there. And then what happened? At time 1, you apply a laser pulse or a microwave pulse. You change my state. Time 2, you apply another pulse, different type of pulse, you change my state. So that you realize the NOT operation, Hadamard gate operation. Okay? So you can see some algorithm saying that I need to apply 1 million gates. That is true. And then you worry, oh, how am I going to lay out my circuit with 1 million gates so long? That is a problem in classical computer. In quantum computer, all you need to worry is that I need to shoot 1 million pulses onto that qubit. So your chip is still that size, but you just keep shooting different pulses. So this is the flow of time instead of space. And as I said, they must be reversible. So I rotate the qubit in this direction, I should be able to rotate back, okay? Until I do a measurement. What happens when I do a measurement? It collapses. It becomes the basis state. Let me show you again. Do you remember this one? I do a measure, I get 0 and 1, right? Once I get 0, I don't know what was the original value. It collapses. Now, this is a very important concept, okay? And we will look at how to do the measurement, okay? How do we implement the qubit? It can be a linear combination of happy and sad, right? In principle, but that's not a reliable one. Now, what we can do is, for example, we form a quantum well, and then we have some level, and then the electron can be spin up and spin down. These are the basis states. And then this electron can go into a superposition of these two states. Okay? And that is a general state. We also have a photonic qubit. Some photonic qubits are like this. You have two paths for one single photon to go through. If these two paths are symmetric, completely identical, you don't know which path you go through because you solve the Maxwell equation, it's the same. But if you do the measurement, you either measure in the top path or the bottom path, right? Because you only have one photon. You can only measure, one of them will show you that the photon is there. And that is, again, you can say, the photon is, the state is a superposition of path 0 and path 1. Basically, it's just like saying that I'm teaching in this classroom and another classroom at the same time. The reason you see me because you make my wave function collapse. That's why you see me, I'm here. Otherwise, if no one come to my class, I can tell my chair that I'm teaching 2 classes at the same time, right? That is a general state, okay? But we will spend more time on superconducting qubit. What is this? This is something called transmon qubit. We will discuss in detail, and it's mathematics. It's just a capacitor here, and then we have superconducting island. So in superconductor, all the electrons become something called Cooper pairs, right? They have 2 electrons, opposite momentum, opposite spin. So you can have 1 or 0 extra Cooper pair in this island. And just like this case, we can say that its basis state is no extra electron versus no extra Cooper pair versus 1 extra Cooper pairs. It can also be a superposition of this. We don't know whether it's 0 or 1 until we measure it. And we use this superposition to do the computation, right? This we will go into detail. But you see that if you look at this, right, we try to distinguish their states, we need to go to very low temperature. Look at this, at room temperature, in terms of EV, is about 26 millieV. In a superconductor, the separation is as low as 20 millieV. So when you cool it down, for example, use the dilution refrigerator, this is 10 millikelvin. Otherwise, your vibration, your thermal noise is larger than your qubit separation. You even don't know which state it is in. And they can lose their information quickly, and that's why it has different type of decoherence time, T1 and T2. T2 is called defacing. We will cover this in detail also in this class. I still have 2 slides. Give me 2 more minutes for this part, right? There are lots of error in quantum computing due to defacing, right? But there's one thing I did not tell you. In quantum computer, you cannot copy information. There's no way you can copy. Remember, you can read it, but then you collapse. You don't know what is the information. And even you find out a mechanism to copy, theoretically, you cannot copy. There's no cloning theorem. So in classical communication, we have many copies to help us to avoid the error, right? Using majority vote. Like here, 0 becomes 0, 0, 0, 1 becomes 1, 1, 1. So even one of them flip by majority vote, I still know this is 0, this is 1. What we do here is use the so-called syndrome checking. We form some entanglement circuits. This is the information we want. If this one get corrupted, you will change the bits that we call it auxiliary bit that we are going to observe. If we are going to measure this one, we find that this is wrong, then we know that what type of error it happened. So we will cover this at the end of the class, okay? Finally, I just want to, after all this, you see the most important thing about quantum computing is what? Superposition. And it has a lot of information, so much that actually we cannot read all of them. We don't have enough memory just to store the state of 300 electrons. So you cannot expect it to do the regular arithmetic for you. But however, we can use some destructive and constructive interference to get the answer we want. So this is the main thing. For example, to check if the function is balanced, right? Find the period of the function, which we will not cover in this class, but just remember that while you can do a lot of things, you still cannot get all the information. So you come up with some clever tricks, right? So in my opinion, the best is that to combine classical computer and quantum computer, and that can speed up. So I think quantum computer can be an accelerator, but $1 trillion business accelerator for our classical computer. Okay, I will stop here. For this one, maybe I will briefly go over in the next class. Okay, I exceed 2 minutes. Thank you.